All right, so today's class will be about one topic, and that is radiative diffusion. Okay, so in our description now of the specific intensity as our main macroscopic quantity and the radiative transport equation as the main equation that we normally solve in order to get our information. We dealt the last time typically then with some sort of system. We have a medium here, gaseous medium, and then we talked to some extent on how if we're an external observer, then the radiation, if this is a very opaque medium, that we actually see is essentially from around these layers with an optical depth of unity, right? These are opaque layers that we cannot essentially observe directly. We're forced to use indirect methods if we want to study them experimentally, that is observationally. But there are also instances where we need information about these very opaque layers in order to build up a sufficient description of the astrophysical system. Okay? Now, if we think about this layer here as some sort of boundary layer, we can call it, separating the opaque interior with the essentially free-streaming limit up there, then of course this represents something like material which has an optical depth much, much greater than unity. But of course, if we take the most classic example for an astrophysical system, a star, then we know that the energy is generated in the core, nuclear fusion processes. But then it gets, of course, transported all the way from the very opaque core to the surface, and then it escapes to us. We see the stars. We see our sun. Okay. So the energy has to go out from this all the way to this boundary layer, even if we cannot see it. So if energy then is transported by radiation, it means that it cannot be in complete equilibrium, because then we know the flux would be zero. It would be Planck body and it would be isotropic. So we have to have small deviations from this. Yeah? And I'm saying now that we're neglecting alternative modes of energy transport here. That is, if you have enthalpy advection, so-called convection, that is not the topic for today. Today we're going to look at the radiation part for this opaque medium. And it turns out that this can be very well and conveniently described as a diffusion process. This diffusion process then is actually the photon equivalent again to the matter diffusion, or as it's often called when you study, for example, in your PDE course or in mathematical physics, the heat equation. And we will come to that description later, as derived also from a random walk, in this case, of photons. Okay. I will just make one remark before we begin, and that is that when I say that tau equals to approximately 1 to surface, that represents our boundary layer, where this is not a good approximation, the diffusion description that we'll do today, I neglect the potential issue of scattering. Now, scattering in this, remember we talked about this, that you can have absorption and emission, and that means that essentially the radiation gets absorbed by the gas, and then of course it delivers energy to the gas, then can be re-emitted, so the matter can re-emit, deliver energy to the radiation field, and then we have an exchange there. Now, of course, if we have scattering instead, so for example, I have, I don't know, a free electron here, as we will look at, and then we have an incoming ray of radiation or a photon, and then it's just scattering off here. Then it's not necessarily any energy exchange between the material and the radiation field. There can be momentum exchange, but not necessarily any energy. And that complicates this picture quite significantly, because you can easily imagine that then it can mean that, you know, photons can be scattered essentially from here and preserve the properties of the material from deep down here, where the optical depth is perhaps greater than unity. But if they were emitted and then just scattered around here and escaped, then they reflect the material properties down here and not from tau equals to 1. That's a complicated, and we will simply ignore that for today. It's just a word of warning for you. Now, all right, let's go now to the diffusion approximation, starting then with, again, our standard description now. And this is our complete radiative transfer equation, as we have seen it now many times, hopefully. And again, we're going to do our description of a stationary medium, so ddt equals to 0. And we're going to take that we only have variations along DDC axis, so 1D Cartesian. We could do this generically, you know, it's an extension of what we will do here, but then you already know that the transport equation that we have is mu, the I nu dc equals eta nu for nu I nu. This should hopefully now be familiar. It's the 1D Cartesian, where again, I remember, be aware of the sign here. Here I have not put any, you know, the standard plane parallel approximation we spoke about, where you reverse the axis by introducing the optical depth scale in the other direction. That's not done there. Yeah? We're going to just rearrange this equation a little bit. Writing is that I'm just going to move over I nu there, and then you see that it's eta nu divided by alpha nu, right? Minus mu the I nu dc, and then we have an alpha nu here. Okay. And now we're going to say, okay, we have this diffusion picture, which means that we have to deal with only small deviations from the equilibrium situations. Sort of a requisite here. We will come to exactly what the more precise prerequisite for that this is to hold. You can think of it for now that the optical depth has to be much greater than unity. We will connect this later to the mean free path of photons, which has to be small as compared to the typical length scale over which macroscopic variables such as density, temperature, etc. vary in the system. All right. Small deviations around the equilibrium situations means that, okay, so we know what the equilibrium situation is. We can call this the 0, that I nu 0 is the equilibrium. Then we know that this is just then the Planck function, which was then just the source function, of course, and eta nu alpha nu 0, 0, we can put 0. This was the equilibrium description that we had before. So, okay, to obtain then a first order approximation, we just need to insert that on the right-hand side to get the first linear approximation of this, which, as you can see, is just then B nu minus nu dB nu dC divided by alpha nu. All right. Well, that is our radiative diffusion equation. We're done there. So that was today's class. No. We're going to work with this equation now. Now, of course, you could potentially include higher order terms here. You would just repeat this. You would just take this one now and insert it again. Then you would end up with the second order derivative as a correction, a third order, etc., etc. But there's no real point in doing that. This is the standard first order diffusion equation that we're going to use. Okay. So let's look at some quantities then of this and what it actually means to have these type of small deviations. We see that we have a deviation directly that depends on the gradient of the equilibrium value, which in this case is the Planck function. And it has the opacity, it has the angle there, which is a geometric effect, right? And it has the extinction coefficient, of course, there. We can start with the energy density, right? The energy density we know now very well. It's just 1 over c. I knew the omega, where I will just now keep the frequency, so we don't frequency integrate at this moment, okay? So that's just 1 over c then. There's only a mu there, so we can directly take out the 2 pi. Then we have mu minus 1 to 1, right? And then b nu minus mu dB nu dc alpha nu d mu. Okay. So here I have to make another remark. And that is that the rest of the results that I obtain now actually relies on that I can assume that the extinction coefficient here is angle independent. That is, that it's isotropic. Okay? Now, when is this the case? Well, it is the case in, when, for example, when we have the static medium situation, that is that the bulk flow is not moving, the bulk velocity is 0. Okay? If we have a bulk velocity, which for example is often the case in the type of outflowing stellar winds that I study a lot, then this has an angle dependence in it. So then again, in order for this to hold, you have to transform yourself into the frame co-moving with the fluid, the Lagrangian frame, if you will. All right? Otherwise, you have to deal with that annoying angle dependence. But like I already said when we introduced the radiative transport equation, we're going to make life easy for us now. Just assume that we have a static media so that we can take this out. All right. Let's take this out. What do we see by this equation then? Well, this should be familiar to us now, right? It's more or less the same argument as we have used for a couple of weeks now. There is no angle dependence in B, right? Right? We assume there was no angle dependence in there. Then we have a mu integral here, and that's an uneven power of mu. The interval is even, so that integral will be 0, as I got from the audience. So this one vanished, and the only one we're left with is that. Okay. And B nu is angle independent, as we know. That's the Planck function. So this one is just 4 pi B nu divided by C. Okay? Or if we frequency integrate this now, well, that's sort of a trivial frequency integral, I would hope. It's just 4 pi divided by C, B, which is just 4 pi divided by C sigma T4 divided by pi for sigma C T4, which we called before A T4. It's the equilibrium value. So the energy density, or the mean intensity, if you prefer to work with that, that's just the first angular moment of the specific intensity, is unchanged in the diffusion approximation. That's the first result. All right. Let's see what we have now. We're going to do this instead of taking the first moment, because that's going to turn out, as you perhaps already anticipate, to be the more complicated one. We're going to take the second moment, the radiation pressure. Okay? The radiation pressure in this situation, we know that it's just the PCC component, yeah, which we just call the radiation pressure. Remember? Yeah? And then we're just going to do the same thing. Okay. So what integral do we have? Well, we have 1c. We can already take out the 2 pi. I hope we can agree on that. The minus 1 to 1. Correct me for all the errors I'm doing now. B nu minus mu, the B nu, the C, we have our alpha nu. But now we have the mu squared, of course, here. And then we have the mu. Okay. We're going to apply the same argument. What happens then? Well, we sort of have 1 mu there, right? And we have 2 there, so this cancels again. It's an uneven, right? So we can see where this is going. All the even moments cancel because the integral becomes uneven, this one here, right? We could continue, but I don't know what to call those terms, you know, the third and the fourth and the fifth. Normally, we just work until radiation pressure, and we close it there. Anywho, now we get 1 over c, 2 pi, b nu we take out, and then there, this integral is just mu squared minus 1 to 1. That's mu cubed 3 to 2/3, right? So that's 2/3. So, okay. Well, we see what this is, right? This is just E nu divided by 3, right? Or if we just do the trivial frequency integration again, we get that P equals to E divided by 3, which was again the equilibrium radiation that we had, the same. So then again, also, the second moment, the pressure is not changed in the diffusion approximation. This is, of course, very convenient. All right. Well, now we're going to do the first moment. So we have already said in the beginning of our class that, well, we need some sort of way to get out an energy transport. An energy transport is sort of a flux. So let's see if actually we're going to find something now for the flux. Because we recall ourselves, what was the flux in the equilibrium situation of a completely isotropic radiation field? The flux was, sorry? 0, indeed, from the audience. Very good. Now we're going to see what we find. Question is, where are we going to do this? Okay, let's hope we remember this relation. If we don't, you have it in your notes, so that's all good. You can help me. All right, so again, we're going to use our previous knowledge, and we're directly going to go to the flux in the C direction, which we denote as deflux. Yes, and all right, so that's the first moment now. But, of course, there will be no phi dependence. We have B nu minus mu d B nu dc alpha nu mu d mu. Okay, well, right. So what happens now? Well, it's the first one that's uneven. right? So this one now, because B nu still doesn't have any angle dependence in it, so it will just vanish. Okay? But this one now has one angle dependence there and one there, so that turns into 2. 1 plus 1 is still 2, I hope. Which means that that won't vanish. Again, we're going to rely on that we can pull this outside the angle integral. We get a minus sign there as well, which is sort of important. And then, yeah, the gradient of the Planck function in the c direction, of course, doesn't really have any angle dependence in it. This we have assumed it doesn't. And then we should have something left, right? Yes, we have mu squared, the mu to solve. That's the same as we had before, right? And it came out at 2/3 then, so it should come out as 2/3 now as well. 4/3, and there we have the flux, right? So, you see that this is it, but we know that 4 pi hat 1 over alpha nu, okay, and then we can write this as B nu dt dc, because we know at a fixed frequency the Planck function is just a function of temperature, right? So what do you see here? Well, you see that the flux, the given frequency here, is proportional to negative of the temperature gradient, the transport of heat. Okay? So here we do get a negative flux, provided that we have a temperature gradient. Also important, it's a negative sign, right? So what does this mean? Well, it means that, let's say we have our star again, and then we want to transport energy from the deep layers out to the surface by means of diffusive radiation. Then the flux has to be positive, right? Upwards. What does this mean for the temperature gradient? Well, that has to go in the other direction. So it has to be lower temperature higher up, higher temperature further down. Well, the temperature increases inwards. This is the simplest way we can understand that in the object. In the case that the radiation transports the energy flux outwards. All right. So next thing we're going to do is that we're going to now frequency integrate this, but now this frequency integral is actually not trivial since it involves the opacity, right? And that opacity in general has a strong frequency dependence in it. So we're going to have to be a little bit careful here. We're going to write this as 4 pi 3, the temperature gradient we can take out, right? But the rest has to now remain in. So we get this integral to solve. 1 over alpha nu dB nu dt d nu. Okay? So what can you see from this integral? Well, actually now, the total flux here is transported out, and it of course depends on this frequency integral. But what you can see in terms of the opacity is that this contribution is going to be smaller the higher the opacity. It's an inverse mean, it's a harmonic mean. We can get it. The lower this one is, the higher the contribution. The higher this one is at the given frequency, the lower the contribution. Okay? So this is equivalent to, say, light transport. Say if I have like I have a pond, and I'm standing on top. I look down the pond, okay? And then you have a light source coming from beneath, all right? And then you have a muddy pond, so you have this mud spread out over the whole pond, and it's optically thick, so you can't see anything, right? From beneath the pond. But then you take the same amount of mud, and then you squeeze it together, and you push it into a corner. Then suddenly, you have the same amount, but you have light escaping from parts of the pond, okay? It's the same amount of mud, but now actually some light escapes through. We call this a porous medium, okay? Now here you can call that it's porous in frequency space. That is, in frequencies where the opacity is lower, more light will slip through, and in frequencies where the opacity is higher, the extinction coefficient is higher, less light will slip through. This leads to effects like if now we think about, okay, but the total radiative flux has to be preserved, it has to go out somewhere, then this leads to effects like blocking of light in certain frequency band and redistribution to other frequency bands. So, for example, if you work like I do in stellar atmosphere, we have the phenomena of line blocking. That is, we have spectral lines with very high opacities in the ultraviolet part of regions, blocking a lot of the light and then getting redistributed perhaps in the infrared where the general opacity is lower. Okay, so it's just a redistribution there. Now, often you will find this defined as in a harmonic mean called the Rosseland mean opacity. Okay? So that Rosseland mean opacity is just this one written in this form, 1 over alpha r, which is Rosseland, which you often see as this quantity, kappa r times rho, I will on, and that is just then the frequency integral here of 1 over alpha nu, or we can call it then directly kappa nu, dB nu dt, d nu, and then in the denominator you just have this one. Okay? Now this one, of course, is then just dB dt, and that we can solve, right? So this now lends ourselves, before we put down the final description for the flux here, we have introduced this quantity kappa here. That is, we have written the extinction coefficient, in this case the Rosseland, but we could do it also frequency by frequency. That is, write alpha nu as kappa nu times rho, where this is often called the opacity. It is the mass absorption coefficient. We can look at the units it has to have. This was 1 over centimeters, right? This was 1 over centimeters in our lovely CDS units. This is the mass density now. So that is grams per centimeters cubed. So you can see that this must then have centimeters squared per gram, this kappa quantity, or the opacity or mass absorption coefficient. This was then aside. All right, so now we can write this indeed as our Fc is minus 4 pi third dt dc, and then we have the b dt here, and we should have 1 over kappa Ross times the mass density. Yes, please.
In the course, you just put 1 over kappa r is equal to that
Yes. Yes, my apologies. Of course, this is, I was just reminded by the audience that, you know, I have a definition, alternative, a unit problem here, because I said that this was 1 over kappa rho, and that's correct, but then I can't put the equality sign here. I have to actually define this. We're going to do this. Very good observation. This is what I mean that we learn together. Kappa rho, like this, and then you have to define kappa rho like that. Okay, and now we see. Now, analogously, you could put alpha Rosseland there. Then you would have to have alpha nu there, right? Okay, very good. Okay. All right, so here we have our expression for the flux. dt dB dt 1 over kappa rho kappa Ross times rho. Okay, so we can choose to write this down in various descriptions. Hopefully they're clear from this. But often you will see this directly in terms of the temperature gradient. Yeah? So then we just need to evaluate this, which, you know, is not very difficult. I would hope for T3 by pi, right? So in terms of the temperature gradient, you will get 16 sigma divided by 3, T3, 1 over a rho there, dt dc, which you sometimes, it's a minus sign, will see as k r dt dc, where this is then called the radiative conductivity. Yeah? This constant in front here. If you prefer to put this as the temperature gradient, right? Now, we could also put this in terms of the energy, right? And then we will again use that we know what the energy is. It is 4 pi divided by c times the Planck function, because we already said that, okay, in the diffusion approximation, the energy density is not changed. That's its equilibrium value. So we know this. So then we can put this term also in terms of the energy gradient. So this will just be dB dc. So that is just then a c or pi, a rho. That is just minus c divided by 3 kappa rho, yeah, times the E dc, okay, which I now will write as CL divided by 3 dE dc. And confusingly, sometimes you will also hear this as a radiative conductivity. So just keep your it is always clear from the context whether we're talking about this form or this form, right? One just have to know what it is that we're doing. And the little L here that I've introduced is 1 over, in this case, the Rosseland, right? But we can also do that frequency by frequency 1 kappa nu rho or 1 over alpha nu, which we know is the equivalent, right? Now this is indeed then what we call the mean free path of photons. And after a break now, we will discuss how this concept of the mean free path of photons together with a random walk of photons, you know, the drunkard's walk, if you will, like this, yeah, can be directly connected to the diffusion approximation here and see if we can learn and gain some more insights from that. All right, take a break.